So, this is the big result. This is the climactic episode of calculus, right? The thing we are most excited for. You know, I'm trying to think of a Game of Thrones. I've forgotten how it worked. The city's crashing. Oops, I hope I didn't spoil anything. Okay, the fundamental theorem of calculus, part 1. We're so excited. This is it. This is everyone's viewing it, turning in to view this. Okay, tuning in to view this. If f is continuous on a closed bounded interval a, b, then this function, the area function that I defined before, is also continuous. The area function is also a continuous function. Not only that, but it's differentiable. And g prime of x is equal to f of x. That's it. That clarifies calculus. That's the big result of calculus. Maybe we're not so excited about it just yet. If so, I completely understand. Okay? I didn't understand why the fundamental theorem of calculus was a big deal, especially this version of it, the first time I learned it. Okay? We'll talk some more about it. Okay? First of all, I can represent it another way. Another way, then, if the derivative of g is f of x, and the antiderivative of f sort of looks like this expression here, I'll clarify that in a minute, then another way of saying this is that g prime of x is equal to d dx. Oops, sorry, let me say it like this. G prime of x, which equals f of x, is equal to the derivative of this function right here. The derivative of this function right here is just f of x. So it's actually this version that I think sort of makes sense in our picture. So let's go back and look at our picture. Remember, what is a derivative measuring? It's measuring the rate of change. If I want to go up here and ask you, how does g of x change? How does g of x change? If I move x just a little bit to the right, what's going to determine how g of x changes? The shape of f of x. So the shape of the underlying function determines how g, the area function, changes. Specifically, since f of x is positive here, as I slide a little bit to the right, I'm going to be adding a positive area. But if f were increasing and I slide a little bit to the right, then each increment I'll be adding more new area. Oh. Yeah. And if f is decreasing, then, but still positive, well, if f is decreasing, then I'll be adding less area as I scoot to the right. So this is saying, what is the derivative of g of x? How does this expression change? Or how does g of x change with time? It changes based upon the shape of f of x. Okay? All right, we will use this. We will prove the fundamental theorem of calculus, maybe. Okay? If I don't get time, I'll make a video and you'll get to watch it, and so we'll see. Okay? I won't hold you responsible for the proof of the fundamental theorem of calculus, but I will hold you responsible for this result. So if I can find a derivative, it also means that the area function must have been continuous. So if it's differentiable, because differentiability implies continuity, then if I know what this value is, if I know that I can take this derivative, then that must be a continuous function. That's not too exciting. Okay, what's the big deal? We've just shown that every function f that is continuous has an antiderivative. So this is a way of representing an antiderivative if you can't find it. Okay? Every function that's continuous, you could go ahead and write that expression and say that's an antiderivative of this function. Now that's usually not a useful way of expressing the antiderivative. It's kind of circular. but that's how you could always represent an antiderivative of any continuous function.